Standard deviation is a key statistical measure that tells us how spread out the numbers in a dataset are. If the standard deviation is small, the values tend to be close to the mean. A large standard deviation shows the values are more spread out. You can see that in the picture as well. We calculate it differently depending on whether we're dealing with a full population or just a sample. When we have data from the entire population, we calculate the population standard deviation. But when we only have a sample, we use the sample standard deviation, which slightly adjusts the formula to better estimate the population spread. This adjustment is called Bessel's correction, and it divides by n-1 instead of n. Let's talk about the formulas for standard deviation. We use two different formulas, one for a population and one for a sample. First, the population standard deviation, sigma equals the square root of the sum of square differences from the mean, divided by n. Let me break that down. We subtract the mean from each value, square the result, add them all up, then divide by n, the total number of values. Finally, we take the square root. This gives us the population standard deviation, used when we have data for the entire group. Now, for the sample standard deviation, it's almost the same, but with one key difference. We divide by n-1 instead of n, so the formula becomes s equals the square root of the sum of square differences from the mean, divided by n-1. Why n-1? It's called Bessel's correction. It corrects for the fact that a sample tends to underestimate the variability of the whole population. Let's compare the population standard deviation and the sample standard deviation. Used when? Use the population formula when you have data for the entire population. Use the sample formula when you only have a subset or sample of the population. Mean used. In the population formula, we use the population mean, mu. In the sample formula, we use the sample mean, x bar. Denominator. For the population, we divide by n, the total number of values. For the sample, we divide by n-1. Bias correction. The population standard deviation does not need any correction. The sample standard deviation uses Bessel's correction, dividing by n-1, to reduce bias when estimating population variability from a sample. Symbols. The symbol for population standard deviation is sigma. The symbol for sample standard deviation is just the letter s. Here's how you calculate standard deviation, one step at a time. Step 1. Calculate the mean of all values. Step 2. Subtract the mean from each data point to get the deviation. Step 3. Square each of those deviations. Step 4. Add all the squared deviations together. Step 5. Divide this sum by the number of values for a population or by n-1 for a sample. Finally, Step 6. Take the square root of that result, and that's your standard deviation. Let's solve a quick example using sample data 5, 7, 3, 7, and 10. Let's begin with step 1, calculating the mean, also known as the average. To find the mean, we add all the values given, and then divide the total by the number of values. Here, the values are 5, 7, 3, 7, and 10. Let's add them up. 5 plus 7 is 12, 12 plus 3 is 15, 15 plus 7 is 22, and 22 plus 10 gives us 32. Now, since we have 5 values, we divide 32 by 5. That gives us 32 divided by 5 equals 6.4. So, the mean is 6.4. Now let's move on to step 2, finding the deviation of each value from the mean. Deviation simply means how far each value is from the mean. In this case, the mean we calculated earlier is 6.4. To make things easier, we'll organize this step in a simple table with 3 columns. 1. Data values. 2. Deviation formula, which is value minus mean. 3. Answer. Let's start with our data values, 5, 7, 3, 7, and 10. Now, we subtract the mean, which is 6.4, from each of these values. 5 minus 6.4 equals minus 1.4. 7 minus 6.4 equals 0.6. 3 minus 6.4 equals minus 3.4. 7 minus 6.4 again gives us 0.6, and 10 minus 6.4 equals 3.6. So, the deviations are minus 1.4, 0.6, minus 3.4, 0.6, and 3.6. Let's move to step 3, squaring each deviation. In this step, we'll take the deviation values we found in step 2 and square each of them. Squaring helps us get rid of the negative signs and gives us values we can use to measure spread. Again, we'll create a simple table with 3 columns. 1. Deviation, copied from step 2. 2. Squared deviation, which means multiplying the deviation by itself. 3. Answer. Our deviation values from step 2 were minus 1.4, 0.6, minus 3.4, 0.6, and 3.6. Now, we square each one. 1.4 squared is 1.96, 0.6 squared is 0.36, 3.4 squared is 11.56, 0.6 squared again is 0.36, 3.6 squared is 12.96. So, our squared deviations are 1.96, 0.36, 11.56, 0.36, and 12.96. Now it's time for step 4, finding the sum of all squared deviations. In the previous step, we found these squared values 1.96, 0.36, 11.56, 0.36, and 12.96. Let's add them all together. 1.96 plus 0.36 is 2.32. 2.32 plus 11.56 is 13.88. 13.88 plus 0.36 is 14.24. 14.24 plus 12.96 gives us a total of 27.2. So, the sum of squared deviations is 27.2. We divide by n-1, not just n. We have 5 data values, so 5 to 1 equals 4. Now, we take the sum of squared deviations from the last step, which was 27.2, and dividing it by 4 gives us 6.8. So, the sample variance is 6.8. Step 6. Finding the standard deviation. To get the standard deviation, we now take the square root of the variance. The square root of 6.8 is approximately 2.6076, so our sample standard deviation is 2.6076. And that brings us to the end of this lesson on calculating the sample standard deviation. We walked through each step carefully from finding the mean, to deviations, squaring them, calculating variance, and finally, the standard deviation. I hope this explanation made the concept clear.